Hello everyone, my name is Harish Chandra and I am happy to walk you through my deep learning capstone project titled DeepFER. This project is a real-time facial emotion recognition system powered by deep learning. The system can identify human emotions from facial expressions with minimal latency and high accuracy, making it practical for real-time applications. As we know, human computer interaction is evolving rapidly. Systems that can understand and respond to human emotions have applications in healthcare, education, customer service, and even in safety. The goal of this project is not just to classify emotions, but to ensure the system is reliable, safe, and able to operate smoothly in real world scenarios. The objectives of this capstone project are threefold. First, to build the deep learning model that can predict 7 core emotions. Second, to ensure safety, meaning no prediction when no face is present, and an unknown output for low confidence. And third, to package the solution into an end-to-end real-time pipeline with an API and a lightweight web application. So in this video, I'll begin with demo to show you the system in action. Then I'll explain the data pipeline, models, and training strategy. Robustness checks explainability with Grad-CAM, and finally, how I package the solution as an API and web application. Let's begin with a quick overview of the project before demonstration so that you can have the thorough understanding of the functioning of the system. Now, DeepFER predicts the 7 emotions: angry, disgust, fear, neutral, sad, and surprise. What makes it reliable is the safety design. If no face is detected, the system remains silent, and if confidence is low, it returns unknown instead of forcing a label. So, with this context in mind, let's prepare the environment for demonstration. So, let me grab the commands that can start the communication between front and back end. To start the demo, I'll launch the FastAPI backend that loads my trained model along with a simple web page that communicates with it. So, first, let me launch the FastAPI. Perfect. So as it is ready to make the predictions, let me initiate the communication command and visit our web page. Great. Here we go. So this is web interface. I chose the ONNX engine, which is faster on my setup. I have also set the confidence score to 0.45. So if the system isn't confident, it will return unknown. So let's first start the test with no face in the view and start the prediction. Now, as you can see, system is currently predicting unknown. Now I'll step into the frame. Now you can see the updating probabilities and here the updation of the emotion class, which is based on my facial emotion. So let me brief you the outputs. So you can see the predictions on the right side and the probabilities of each of the 7 emotions down in the bar graphs. Now I'll try different expressions. For happy, neutral, sad, and surprise, the probabilities update smoothly, though you may notice some small fluctuations between the frames that's expected in real-time streaming. Now, there is also an option for test time augmentation, which averages the prediction with the flipped frames for more stability. But I usually keep it off since it reduces the speed. So that's the system in action. Next, let me show you how I designed the data pipeline that powers this model. So the dataset is organized into train, test, and validation folders along with the simple mapping for the file indices. Here are the folders. So first I ran the data audit to check the sample counts per class, detected corrupted files and flag duplicates. This also helped me to spot imbalance among classes. For example, disgust has the fewest examples. For validation and test sets, I used simple resize and a center crop. For training, I added diversity using rotations, flips, color jitter, rand augment, and light random erasing. I also created a grid of augmented samples to make sure images look realistic. Now, the pipeline is in place. Let's move on to the model selection and training strategy part. So, in order to find the best suited model, I experimented with two most popular backbones for image classification. First, ResNet-50 and second, EfficientNet-B0. Now, EfficientNet-B0 emerged as the best balance of accuracy and speed. So, I used it as my main model while keeping the ResNet-50 results for comparison. Upon finalizing the model, I trained it in two stages. First, in warm-up stage, where I unfroze the first few backbone layers and classifier, trained with the label smoothing to adopt quickly. In second, fine-tuning stage, where I kept those layers unfrozen, used class weighted cross entropy and label smoothing. Again, cosine learning rate, schedule, and occasional mix-up for regularization. Finally, I saved the best checkpoint by validation accuracy and used early stopping to prevent overfitting. Now, let's look at the results and evaluation metrics. Now, let me navigate you to the results of my best model. Here we go. In the matrices, we have the efficient net, this one, this. Okay, perfect. So on the unseen test data, the model achieves around 70% accuracy, as you can see, and the common overlap includes surprise versus fear and sad versus neutral. I also tested the robustness against blur, brightness, rotations, and noise. Mild distortions were fine, but heavy rotation and synthetic noise reduced accuracy significantly. This suggests adding alignment and denoising for future improvements. Now, to validate models' attention, I generated Grad-CAM heat maps. Activation focus on eyebrows, eyes, mouth, exactly where the emotions emerge. Failure often comes from the off-centered faces, highlighting the importance of good detection. So, let me navigate you the few examples. Here are the one, yeah, for this is an example for the angry class. Now, after verifying the performance and interpretability, I integrated everything into a real-time pipeline. Now, as we seen in our live demo, the pipeline is straightforward. Capture the frames, detect the face, then crop, do pre-processing, and pass it to the model and get back the probabilities. Uh, the two safety checks make it reliable. First, if no face is detected, simply no prediction. And if contents is low, then return unknown. Now, with the ready-to-use real-time pipeline, I must package entire system into an API and serve the same via web application. So, let me walk you through this stage. So, I package the system as a small Python module. The FastAPI backend loads the PyTorch or ONNX model, applies pre-processing, and exposes the output via /predict endpoint. The web app streams webcam frame and sends them to the API and shows the probabilities in real time. Because everything is modular, so one can update the models without changing the app, as we have already seen in our web interface. Using ONNX runtime cut interface latency by over 30% on batch 1 inputs with almost same accuracy as PyTorch. So the same export path supports TensorRT on GPU, even for faster predictions. Now, with this version packaged, let me quickly share what I would do next if I had more time. If I got the chance to further extend, I would like to work on the aspects that can help the system to improve its accuracy, including the following. First, add probability calibration like temperature scaling for better confidence alignment. And second, try larger efficient net variants for further accuracy improvements. And third, add phase alignment to handle rotations. And fourth one is explore small ensembles to improve tricky emotion pairs without breaking the real-time performance. So with these future goals in the mind, let's recap the what we just discussed and close this presentation. So, to recap, I walked you through my DeepFER capstone project, a real-time facial emotion recognition system with a solid data pipeline and transfer learning approach. Around 70% accuracy with the test dataset and robust handling of uncertainty. A safe and modular real-time app running on ONNX for speed. Thank you for watching. I hope this walkthrough of DeepFER project gave you the clear understanding of both technical depth and practical design of this project. Thank you. That's it for today. Bye bye.